Alright, so we are going to continue our lecture on aromatic substitutions, and we had just gotten through talking a bit about the naming and then ortho, meta, and para of dye-substituted rings. And so let's start taking a look at some of the reactions here. So let's take a look at some reactions with aromatic rings. So what, at the end of the day, there are essentially two mechanisms at play with aromatic rings. There's electrophilic aromatic substitution and nucleophilic aromatic substitution. The first one we're going to talk about, and the one where we will spend most of our time, is electrophilic aromatic substitution. Substitution. Okay, cool. Now, the name is going to tell us exactly what's happening, right? We're obviously going to be working on an aromatic ring. We're going to be substituting one of the hydrogens for a new functional group, okay? So on an aromatic ring, we're going to be substituting one of the hydrogens, and to do that, we're going to need an electrophile, okay? So we're going to have to generate an electrophile. But the thing is, you guys have been generating electrophiles all semester long. Right? In fact, we've been generating really good electrophiles all semester long, right? One of them being a carbocation. So a carbocation will and can, and we will show it in just a little bit, will react with an aromatic ring and add something to the ring. So we have to be careful about when we generate a carbocation if there's an aromatic ring around, because we can start to do some side products if we didn't want it to react with the ring, right? So, but like I said, we're getting a little bit ahead of ourselves. Let's start with the simplest example. So, right, if we have this, let me draw that a little bit nicer there. Okay, so simple halogenation, right? Simple halogenation. So this will work with chlorine or bromine. I'll show them both in just a second here, right? But the idea is this, right? I want to add a halogen to my aromatic ring, okay? Now to do that, right, I have to have a good electrophile. And just Cl2 by itself is really not a good electrophile, okay? So we're going to have to add something to that to make this work. And we're going to have to add a catalyst. This is one of the standard setups for this reaction. So we have chlorine, our halogen source, and AlCl3. Now, what in the world is AlCl3? Well, guess what, right? Some of you guys might have already guessed it, right? This is an acid. Okay? Wait a minute, you say, there's no hydrogen on there. Well, remember, I'm not talking about a Bronsted acid all the time, right? This is a Lewis acid. Okay, so what's a Lewis acid? Well, it's a lone pair acceptor, right? So to be a lone pair acceptor, you're going to have an open orbital, right, for the lone pairs to come into, right? So we need an open orbital. We're going to want this Lewis acid to be electron deficient. A less fancier way of saying that is we want this to have a partial positive charge would be great, right? If we can make our deficient open orbital more positive, right, then it's going to be easier for this to react. So let's think about this for just a second. Here is the Lewis structure for aluminum chloride, AlCl3. Okay, I drew it like this. We're kind of looking at it from the side on, right? So it's a planar, right? It's sp2 hybridized, so that means it's planar. Right? And because it's sp2 hybridized, that means it has an unhybridized p orbital. And that unhybridized p orbital is sitting above and below the plane of the chlorines there. So those chlorines are basically in a triangle, right? That the chlorines and the aluminum are all in a single plane. Then we have this open p orbital that's sitting above and below there. And that is going to be where the lone pair is accepted. Okay? So something negative, something negative is going to bind to that aluminum. So here's how this is going to work. Okay? What does it mean? Okay? If I am telling you guys, and remember the stuff that I've been talking about all along, if I'm telling you we have an acid, where do we typically use that in our reaction? What's the point of it, right? So remember that typically when we're dealing with acids, they're used in the first step. They're there to get the reaction going, right? So it's not going to be any different here, right? Just because we're dealing with a Lewis acid and not a Bronsted acid, it really just kind of means the same thing for us, right? We look to use that in the first step of our mechanism. So we're going to get our chlorine. We're going to get the aluminum here, right? I'm just going to draw it like this, and maybe you guys will see why here in a second, if you guys don't already see it. Okay. And the first thing that's going to happen, right, is the chlorine's going to bond to the Lewis acid, right? So the Lewis acid is going to accept the lone pair there from the aluminum. Right. And when we do this, we make this adduct here. Ooh, that looks awful. Oops, I wanted this in red. Excuse me. Okay. Right, so we made that bond there, right? Let's clean this up again. I don't like how that looks. Okay, nice. So we made that bond there. Okay, what are the consequences of our actions? We did a thing. Let us analyze a thing. Okay. That's unusual. A chlorine with a positive charge, right? A chlorine with a positive charge. Aluminum with a negative charge. Now, is that chlorine really positive? Is that aluminum really negative? Well, remember, right, in some cases we have to remember that formal charges are there to kind of give us an idea, right? They're to flag something like, hey, pay attention to this. There is something unusual. So let's take a look at this for just a second, this unusual setup here. Let's take a look at this chlorine-chlorine bond right there. Now, to begin with, we know that chlorine by itself, right, to Cl2, that's pretty darn reactive, right? If you just bubble or release some chlorine gas into a room, it's going to react with everything, right? So we know that it's a fairly reactive molecule to begin with. Chlorines don't want to be bound to each other, right? They want to go and oxidize some things and, go through and do this. So that chlorine-chlorine bond is fairly weak to begin with. Now, what is the consequence of making this Lewis acid adduct here? Well, we end up making this bond even weaker here, right? We end up making that bond even weaker. So it's easier to break that bond between the two chlorines here. Here's what I mean, right? So I'm just going to take this guy, right? Bring it down here, right? Let's break this bond. I know I'm drawing this. I'm drawing it like that for a reason, right? I'll come back and talk about it for just a second, right? Okay. And right, we also have our Cl. I'm going to draw these in. Right, do you guys see that? You see what we did here? Now, a couple of things here, right? Is this really going to exist for a really long time? Well, maybe it might exist for longer than you could expect. But really, this is an equilibrium. Okay? Oops. I meant to draw the arrows. Right? Really, this exists as an equilibrium. This species over here is going to exist in a higher percent than the stuff over here on the right-hand side. Okay? Remember, we're talking about equilibrium, so right, they exist with each other, but most of the time it's going to exist over there in the purple. Okay? Now let's think about this for just a second. Let's zoom in a little bit more here, or focus in, I should say. What is this? I don't know why I did that. Let's try this again. What do we notice about this right here? Right? Which is the same as this over here. Well, this isn't. Spelling is hard. Well, these are excellent leaving groups. Okay? This is a fantastic leaving group. And your first question should be, well, as compared to what? Right? So keep this in mind here for just a second, right? Here in green, right? This is a better electrophile. Right? An even better electrophile here, right? A better. Okay. So here's the point, right? Let's simplify this for just a second. By binding the chlorine, right? By binding the chlorine to the Lewis acid in the first step, we generate a better electrophile with the potential of making an even better electrophile with making a good leaving group along the way. Got it? So pause here for just a second and kind of see if you can follow along with my thought here. Because I'm about to show you the mechanism, and then we can put into context what we mean by excellent leaving group and even better leaving group, and all, even better electrophiles, that kind of thing. And I'm going to take a quick pause here too, so pardon the rough edit here for just a second. Okay, so we're back. So let's take a look at the mechanism, and then hopefully it'll make kind of sense here what we're talking about. All right, so we start with our little buddy benzene. Okay. So let's say that we only had chlorine around, right? So the thought is that a pi bond would swing open to hit that electrophile and kick off this chlorine here, right? So in essence, what we would do then, let's start to color code some stuff. Purple, right? So we make a bond from the purple to one of the chlorines, right? And we end up kicking off this here. Right? So this is the idea. Pi bond's got to swing open and hit that chlorine. But this won't happen, right? We're really not, under some very, very, very rare cases can this happen like this. That chlorine, right, this chlorine is not a strong enough electrophile, and this right here is not a good enough leaving group. That's what I mean, right? We need to generate a better electrophile, right? And we need to make an excellent leaving group for this to happen. And we do that by binding the chlorine to, right, to that catalyst. Now, have we seen something like this before? Well, yes, we have, right? When we were talking about how to make our alcohol groups into good leaving groups and making them electrophilic, all this kind of, right? We had the same kind of idea there, right? So really we're not seeing anything different. So how does this actually work then, right? So here is the mechanism, how it works. So the first thing is we generate that Lewis acid adduct, okay? Okay. All right. Then, once we have generated that adduct, I'm going to bring this down here. Pi bond. It doesn't matter in this case, right? And we'll talk about what that means. Any pi bond will come in, hit that chlorine, and kick off that leaving group, right? Kick off that much better leaving group. So let's maintain here. Let's say yellow, right? Yellow and purple and purple. Okay. Now, in this case, does it matter which of those two we added to? No, not really, right? So let's go ahead and just add the chlorine here. That sounds good. And we've got the positive charge there. Right? And then we've got the AlCl. Oops. Cl here, okay? We've got this. What's the problem that we have? Well, the problem is we've got a carbocation, and we broke aromaticity. Oof, right? That's two bad things there. So we need to reform the aromaticity and get rid of our carbocation. And so let's do that. The hydrogen. Okay, this is why I started to color code things. The hydrogen that is bound to the position, right? The hydrogen that is bound to the position where you add the incoming group is what's going to get eliminated, okay? The hydrogen bound to the carbon where you bring in the group, that's what's going to get eliminated. So here's the mechanism, right? We take one of our chlorines from the aluminum complex, we grab that hydrogen, and we slam down a pi bond. Okay? And so our product then, got this, there. There's a chlorine. We reformed this here, right? That pi bond in green. And look what we did here, right? We have our AlCl3 back. Hopefully you guys see that. And, right, what else did we make? Cl, oops, that should be in green. ClH. Okay, so we end up bubbling off HCl. There are the three things that we kick off from this reaction. So we end up reforming our catalyst. The AlCl3, the Lewis acid catalyst. We bubble off some HCl and we add a chlorine to it. Now, truth be told, okay, if you look this up online and in different places, you might see a subtly different mechanism, okay? I'm not saying they're wrong, okay, because they're probably not. It's just there are different ways of representing this because of this idea of equilibrium and all this kind of stuff. Okay? But here's the mechanism. Good to go. A couple of notes, okay? A couple of notes about all this. We can use a number of different catalysts. we can use FeCl3, okay? AlCl3. There's even cases of just using solid iron mixed with chlorine gas, right? And if you bubble those two together, you basically just end up making this along the way, right? So if you do happen to see it written like this, right, it's basically the same thing as just iron chloride there, okay? Iron 3 chloride, right, will work exactly the same way as aluminum chloride will. No big difference in that one there. This also works with bromine, right? So we can have Br2, right, and AlBr3, or we can have Br2, right, and FeBr3. That works just fine. Cool. So that is how we can add one equivalent of a halogen to an aromatic ring. You guys have to know this mechanism, okay? This mechanism, the basic steps of it, right? The basic steps of it is how we're going to be looking at a lot of these other mechanisms. Right? So we can think there's a couple different parts to it, right? So we have this part in yellow up here, okay, where we generate the electrophile, right? We have to generate or create a good electrophile. In green, right? In green, the benzene ring attacks the electrophile, right? And then here in the last step, we reform the benzene ring. So really, those are our three steps. Yellow, we generate the electrophile. Green, we attack the electrophile with the ring. And in black, we reform the ring itself. And those are the three steps that we're going to see over and over and over. Okay? We can do this with bromine. We can do this with chlorine. You can even do this with iodine. Iodine's going to work a little bit differently, though, because iodine is just kind of a different beast. Okay? Iodine's a lot easier. Well, maybe I should say easier. It works a lot differently with generating a good electrophile. And here's what I mean. So if we just have elemental iodine, right? If we do something to it, okay, it's a little bit easier for us to generate that species, or that iodine with a positive charge. But what we're going to need to do is typically add some kind of oxidant to it. Okay? So this just means some kind of oxidant, some kind of oxidizer. There's a couple common ones. One setup, I2 over nitric acid. That'll be just fine. I2 over some kind of copper species. Some mercury salts work. Right? Some different copper salts work. It's not too hard, right? But then the same mechanism happens here, right? We generate an excellent electrophile, the ring attacks, and then the ring gets reformed, okay? That's really all there is to it. All right, that seems like a good place to start up the first video, right? This is the, we'll pick this up in the next video. We'll continue with some more reactions, continue with some more mechanisms, and then start to discuss some of the more complex sides of this.